Okay, let's dive into function values and anonymous functions, still in chapter 9. Um, okay, so let's start with this concept of predefined functions. So ML, the language, the system, um, has a bunch of, predefined variables, and then some of those are bound to functions. And there's a concept we're going to kind of get to, which is this notion that functions in ML don't actually have names, but we bind them to things. And what that means is, and you gotta again separate yourself from your Java, C++, object-oriented kind of world, your imperative kind of world where there's a function and it's called this, and there's just no notion of defining a function and not having its name. I mean, compiler theory, requires there's a symbol table, and the name of that function is one of the symbols, and it kind of has to be like that. This is what we're used to, and but the concept in ML is that there are these functions, and we connect them to things we know, like the tilde, right, for negation, or the ord, which returns the ASCII code, right, for a particular character. By the way, the ord is back there in a table on page 72 of the book in chapter 5. It's a long ways back, maybe, and so just remember that that was one of the little functions we were given, right? And but it doesn't have to be called that, and we can use the concept in really cool and powerful ways in ML. So what we can do, and this is just a little bit crazy, really. We've talked about before using fun, right? This fun notation, which allows us to define, new named functions, right? There's its behavior, and I'm gonna bind it to this name out of my convenience. Well, it turns out that even something like the tilde, right? This guy right there, um, that guy is a negation function. So I can literally just assign it. I can create a value. I'll call that value x, and I'll assign it the tilde function. In other words, there's a whole function on the back end, right, that works and makes the tilde do what the tilde does. I can just simply say, I want that to be called x now. I want a value called x that has that's bound to that. And then having done that, if I say x3, it's exactly the same as if I've said tilde 3. I get -3 as my result. This is a little bit kind of mind-blowing. It's also why I have kind of insisted earlier in the programming projects, writing these little ML programs, little functions, that you get away from trying to write them in ways that look like you're, message passing, calling a method of an object, or you got to get away from that idea, and kind of get more comfortable with the ML syntax, so it kind of liberates you and liberates your thinking. This is kind of a good example of that. So this just reiterates this concept that the functions themselves do not have names, okay? But they may be given names by way of binding them, okay, to variables. And so when you use this fun syntax, right, and you declare a function, right, fun f, here's an example that we'll get on the next slide, but it does two things: creates the new function, and then binds that value to a name, okay? And the function itself is a value, and I can bind it to a name. So here's an example. Here's an example of named function versus an anonymous function, okay? In the named function, this is kind of what we're used to. There's fun as a keyword. I've got f, which is the name of my function. F expects an x, and it's then going to return. It's going to evaluate to x plus 2, and then here's the type, right? ML always gives us our type. Then I can, which basically just increments the value by 2. I can now say f1, and the answer is 3, because what this guy does is increments the value of whatever comes next, okay, by 2. But I can also do that as an anonymous function without ever calling it f. So in this case, instead of the fun keyword, I use fn keyword, okay? Fn, which is interesting. It's the same keyword that I use when I'm seeing what the type is, right? So now I say fn, I can say fnx, right? And then I use the match, um, that pattern that we've already seen before. And what match basically says is, if I see something that looks like this thing on the left, I'll do this thing on the right, right? That's how the pattern matching works, and that's what the match does. So it's basically says, if I see an X, and I see the addition now, and I'm going to, and the way the 2 is, and I infer that that's going to be an integer. If I see an integer X on the left, I'm going to increment him by 2. And that's kind of what that does. Well, I don't have to name that anything. I can just know that that's what it is. Then I can shove it in here and just put some parens around it so that I have precedence all wrapped up. Then everything, and this is so weird, and I know that this is a little mind-blowing, but everything then inside these parens is a function value. And it is the function that takes some, that for some value x, it evaluates to that value plus 2. So I can basically just encapsulate it all here, and then having that right there, and then the 1 works exactly the same way. And this is, again, where you've got to get away from that feeling of writing, code that looks very imperative, very function call-ish. I know it's ironic because this is functional programming, but that procedure call, function call thing you get in imperative languages and in object-oriented languages, right? We call them method calls, right? We call them message passing. We call them different things, but this is very much a different kind of a feel. The other thing that this reinforces is a principle of functional programming languages, which is that functional programming, in functional programming, the functions are first-class citizens. They can be anything. They can do anything. You can create them. And we'll kind of get into that a little bit later with higher order functions. But you begin to see that here. I just can construct this thing on the fly and not even give it a name, and I can still use it. Crazy, but this is functional programming. So this is where it starts to get a little more hairy, but again, you need to kind of hang with here, and go back through and do these examples again in the book and read it again until these ideas begin to distill out. Okay, so we have this match syntax again, if you remember. And that's kind of what we're using. This guy right there is our symbol that we use for matches, okay? And what I can do is define a function expression as fn followed by a match, okay? So here's the kind of the key ideas. We get, when we use fn instead of fun, when we do fun, we have to give it a name, and then we have to give it a parameter. With fn, we don't have to give it a name. Well, we can't give it a name. It's an anonymous function, okay? But we can still, define the functionality, okay, without having to define the function itself and give it a name in the traditional way. So here's an example. These two do the exact same thing in ML. Let's look at the first one. The first one's kind of what we already know. I got a function. His name is f. This is the one we just looked at, right? There's an x on the left, and then he wants, x plus 2. What I do now is, I'm not defining a function, I'm declaring this value, and I'm naming that value, and that value's name is f, okay? So the equal sign basically just says everything on the right, all of this is the value of f, okay? F is value, and this is its value, starting here with fnx. Now, again, this looks like a long string of like, okay, f equals fn x equal x plus 2, and you gotta break it down into its chunks in order to understand it. So f is a value. Everything on the right-hand side of the equal sign is its value. What is its value? Its value is it's a function. And in particular, it's a function that employs this matching pattern. When it sees one of these, it gives you one of these. I see an x, I give you x plus 2. Okay? Therefore, I have in fact declared, created via this function, this anonymous function on the right, but then I've actually bound that to the value f. But I had to do that explicitly over here. And it's not as automatic here as what you get when you use the fun keyword. So here's another example of using anonymous functions. Um, so the classic, application is I have a small function and I only need it in one place. And so, for example, I've got quicksort, right? And the quicksort, by the way, it's used extensively in Chapter 9, and it was a homework assignment in Chapter 7, but it's actually not one that I assigned. It was exercise 7 in the homework assignment little thing there on Canvas. I actually just dropped a quicksort function in there that you can use. It'll make this thing a little easier. But anyway, the idea here is that the way quicksort works is I pass it a list and I pass it a comparison criterion, okay, a function basically that sort of just creates a Boolean result, right? So I can say, int before, which basically says A comes before B. Well, how does that work? That's defined by A is less than B, right? And you can see that int before is a function, takes a tuple of ints, returns a Boolean, okay? So that's int before. And I've got to have, for quicksorts, this quicksort algorithm or function in particular, I've got to have a function that allows me to tell which one of these two items comes before the other one, okay? So that's how I do it when I just declare it the way we've learned it so far. But with fn, where I can use anonymous functions, I've got this sort of a declaration right here where I've got quicksort, there's my list, and well, it wants a function over up here. I just said int before because I already declared that function. Here, I skip all that stuff. I just go fn, and then I just provide the match right there. What's the match? The match basically says, you give me a pattern that looks like this, an A and a B and a tuple. I'll give you a true or false on whether A is smaller than B. That's it. And then again, here I can do it the other way with greater than, but I can just create these functions. And then you got to remember that there's a match going on here, fn and then the match. And I'm pattern matching is what I'm doing there, okay? That becomes really critical. Otherwise, you just get bogged down like crazy in the syntactic soup. And you've got to know in your mind what that's trying to be and what it's trying to say. And then finally, in this section, we have this op keyword, okay? And what op does is actually super cool. And you can kind of see here as an example. Okay, let's start with this notion that we've got operators, okay? And as we talked about, every function in the system has a value, and we just happen to bind it to certain names. Well, we can actually pull the value out of it, okay? So when I say op, what that does is it takes this thing, like in this case the asterisk, or in this case the less than sign, that is a name, okay? That's a name in ML. It takes that and it evaluates to the value of the function bound to that name, okay? So what you can see is I go op star, and it goes, oh, you know what the value of that is? It's a function. And it takes a tuple of two integers and returns an integer, right? So it's the multiplication, they got this quicksort. I can now drop the op less than, and there's my function. So I want to do the less than. I don't need to go tuple a b, right, and then the arrow symbol, and then on the other side, give me whether a less than b and do the true thing. I just need the less than function. Well, op and then that less than sign returns the value of that function, meaning the function itself, without its name, just the function itself. And again, that's a little bit of a mind-blowing concept, the notion that there's just this function floating around, with its logic and its structure, and there's no name associated with it. That is really, really radical. But again, there we are. That's ML.